So, all right, so those are the tests that we do when we are drilling the shaft, when we are constructing the shaft. Now we're going to pass to the last three, which is, or the last four, which is the ones that you do when the shaft is constructed. This is what is absolutely new, or let's say new in the last 20 years, 15 years, because before we didn't have any of this technology. So the drill shaft was constructed, and then once it was constructed, that's it, right? I mean, you leave the site and you pray that the shaft is never going to collapse, and that's it. Uh, Now it's a different story. And I always like to talk about that because I think the more you look, the more problems you find. And probably before you have those problems, but ignorance is a bliss. And by not knowing that you have the problems, you never address them. And I guess you have a good factor of safety that it took care of those problems and it was never an issue. But going again in the mentality of LRFD, knowing that we need this quality control and all that, we need to do a better job. So that's where these tools came. The first two we're going to talk is the CSL, which is the cross-sonic logging, and the thermal integrity profile, both designed by the same company, by Pile Dynamics, here close in Cleveland, and GRL. And it's interesting because they created one and they invented the other one that basically kind of replaced what they invented before. And then we'll go into the old school, which is the concrete coring, and we'll finalize with the OSL test. So the first one is the CSL. CSL, cross-sonic logging. It's been around now for a while. It's a really good technology. Basically, what you do is when you construct the shaft, you leave some access pipes. What I'm showing on the picture on the left there is the rebar, and you can see some black pipes. Those are steel pipes. You could also have them as PVC. And those pipes basically just allow you to, later on when it's constructed, to be able to lower some sensors. So what you do is that you roughly do one pipe per foot of diameter. So if I have a shaft that is 5 feet diameter, I typically put 5 evenly distributed pipes for access, right? So once you have those access and you put the concrete and the concrete cure, right, then you lower the sensors. So what you see on the right, one is red, one is black. I put one sensor and look at the drawing on the upper part of the screen. I put the sender of the wave in pipe number 1, and then I put the receiver on number 2, and then I lower the 2, and I constantly send signals, right? I'm sending compressive waves as I go down, and I measure the time that it takes to arrive. Then, so I do 1 and 2, then I do 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then I do the same 2, 1, 2, 3, 2, 4, and all that. So couple comments here. The one that is extremely important is when you do CSL and when you have these pipes, you always have to fill them with water. Sometimes people forget to do that, and then you have the bonding. So the problem is when the concrete cures, if you don't have the water inside these pipes, the temperature change is going to be significant, and the pipe could detach from the concrete. So you always put water and you lock it, and then once the concrete is there and all that, you remove the water and put your sensor. So that's more on the practical aspect of how to perform the test. And then the second part that I have seen a lot doing presentations in South America and Central America is that the standard really requires you to do 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, then go to 2 and repeat. Even though you already did 1, 2, you have to do 2, 1. It's the same reading, right? Before you did it, measure it from 1 to 2. Now you're sending the wave from 2 to 1. But in order to have the complete data, you have to do it. Now, why in many countries and places it's only done half? Because of time. This is a very time-consuming test, right? You have to lower the sensors, and then you have to rotate and all that. Doing one shaft, if it's a long shaft, can easily take you a morning or a day, right? So you can see where the test, even though it's a really good test, the implementation sometimes it's a little tricky. Now, given that the company has come with different methodologies, one is that now they have like all the sensor at once and they just lower everything at once. So that could be a response to that, right? But anyway, so looking at the results of the test, because they are extremely interesting, these are the kind of profiles that you get. So if you look on the upper part of the screen, you can see that we are shooting signals from pipe 2, and the result that we are showing is from 2 to 4, then from 2 to 5, and then from 2 to 6. So basically we have the sender on 1, and then we're looking it around. And what you look is 2 profiles. So each plot, it's a different combination. And you have two plots. One is plotting energy that is expressed in decibels, and the other one is plotting time. So it's basically how much time it takes, right? Now, this is what I say, this test, to me, and my interpretation, is typically what you're looking is for contrast. What you're looking is to see when there is some kind of behavior that is different than the rest. I know that if you are measuring a compressive wave and you are measuring the time, you can determine the speed, right? And if you have the speed of the compressive wave, you can try to correlate it with something. But in this case, we're not trying to do that. What we're trying to see is looking at what depth I have a change. So for example, in this particular example, when you are at depth of 24 feet, you can see that there is a massive reduction of energy and there is a significant increment on time. So what it
Yeah.
means is something is going on at that depth, right? Which is very close to the bottom of the shaft. Something is going on at that depth that is basically not allowing the wave, the compressive wave to travel through, right? I mean, it's delaying it and the energy is being lost. So what is the first thing that comes to your mind when you are doing this? Sediments, right? I mean, if I have a concrete that is bad quality, or for some reason I end up with a pocket of sediments that could not, because when you do the tremie grouting, when you put the grout on the concrete, you do it with the tremie method. You start from the bottom and you basically displace everything by putting concrete. So if some pocket remain there, if some bubble remain there, you will see this kind of behavior, right? Because the sediments are going to slow the compressive wave and they are going to dissipate the energy. Now, there is a reason why we do compressive waves, right? Because you can have water. So the compression travels in water, the shear doesn't travel in water. So, typically you will see it with a compressive wave. There is, of course, ASTM standards that tell you what could be a problem, what could not be a problem. They say like the first arrival time, if you have a delay between certain percentages, it could be an anomaly or it could be a flaw or a defect. It also talks about energy. I always like to bring this and make people aware this exists, this table exists. But in my opinion, what you're looking here more than the table is just that contrast. What we looked before, how do I see when the energy is lost? Because that's really what is going to help me to understand where the problem could be. Now, not only I have the advantage to see this on a vertical profile, but because of the information, I can do kind of the equivalent of tomography, right? I can generate like a 3D view of this and identify where these spots could be, right? Where these voids or where these cavities could be. In this case, for example, it's called like a heat map, has nothing to do with heat, but it's just showing where the speed gets really slow on this. And you can see those red areas. And that's probably where you are looking at a problematic place. Now, passing into the next one, what do you think could be the problem with the CSL? One, time, right? Because it takes time to do the test. The second one, which is probably one of the main limitations, is I'm only measuring speed and waves within the pipes, right? I mean, I have the pipes put to the rebar. So it basically, I'm only looking at the quality of the shaft inside of the rebar. That's great from a structural point of view, but as a geotechnical point of view, I don't even care. The part that I care the most is the concrete with the rock, is the contact between concrete and rock. And with CSL, I'm not seeing it.
How can you know that?
Exactly. With CSL, you can't. You can't because all your waves goes inside.
Yes, the CSL is for cross hole. It's a cross hole.
Exactly. So then, I mean, for a while on the West Coast, they have been using gamma radiation. So with gamma radiation, you basically have like a similar access point, but then what you do is that you send a radiation and radiation goes on both sides. So typically allows you to see what is your thickness and your cover. However, I don't think anyone is interested in working with something that is called gamma radiation, right? So the true answer that we have, and it's the same company, PDI is the one that invented this. They go with something that is completely different, that is called a thermal integrity profiler. And this is a really, really smart idea. So what you are doing here is that you are using Laplace equation, and I know we don't want to go into discussing Laplace equation and a second order differential equation that is being integrated, but just to kind of go back into what we know, right? We all learned Laplace equation when we took soil mechanics and groundwater hydrology, groundwater geology, courses like that. We all learn how to do flow nets, right? And basically what we know is that if you know the flow of something, right, you can start apply, Laplace equation. And in this case, the flow is heat and is based on concrete. And just to simplify it tremendously, what we're saying is if I put a volume of concrete, because that concrete is going to generate some heat, I should be able to predict what is the temperature at different points of the shaft. Similarly, if I have the temperature at those points, I can back calculate and say what was the equivalent diameter of the concrete that I put, or the equivalent radio of what I put. So the technique itself, it just works with these cables. So you see these cables that are yellow, and they have sensors, right? So every yellow cable that you see has a little white thing. That white little part, it's a thermometer. It's basically, let's call it a thermometer. It's not exactly, but it's like if it was a thermometer, and it registers the heat, right? So by having these across these cables, you know the temperature at different locations. Now, this is super practical because the cable can bend, it can accommodate to anything. You can put it on the CSL pipe, you can put it on the rebar, you can put it anywhere you want, right? Now, one of the disadvantages of CSL is that you have to wait until the concrete is cured, right? In order to be able to do the test. This one happens. So typically, to wait until it's cured and all that, it means that you're going to do a CSL a week later after you pour the concrete. In this one, you are only looking at the peak of heat, which typically happen only like 2 days or 3 days after pouring. So it cuts the time that you wait. But also, most importantly, you don't even have to be there. On the other one, you have to go and put the sensors and all that. In this one, you just put the cables, you put a data acquisition unit. You can even leave it there, or you can connect it to a modem and get it to your office. But the point is that all the data is being acquired by the system. You don't have to do anything. And then at the end, you will get your results. So it really expedites the process. And obviously, as you imagine, this reduces a reduction of cost. So what do you see with this? So when you do the double integration of Laplace and you come up with an equivalent volume or an equivalent size of concrete, you are going to see a plot as the one that is on the left. If you look the upper part, it's telling you what is the radius of the shaft. Now, this is not the physical radius. The physical radius, you measure it as we talked at the beginning with the sonic caliper or with something. This is an equivalent radius that corresponds with a volume of concrete that generates the heat that you measure it. And what you see on the right is different cables. Every curve, it's a different cable located at a different location of the shaft that is telling you, based on that radius, based on that sensor, what is the equivalent radius. Now, this is a great example that you can see if you look the line that is shaft, right, it's about 30 inches. So that means that was the diameter or the radius of the shaft, 30 inches. That was the size. And all of the cables predicted an equivalent radius that was bigger than that, right? Which means in some cases it could be actually bigger, but in reality what it means is not that it's physically bigger. It's just that the cement that you have was probably higher or better quality. The content of cement was higher or better quality, that it produced more heat than what you were expecting, right? It's all good. In this case, it's all good. All your radius are bigger. You can also go and do like cross sections, which is what is shown on the right, and you can see that your equivalent radius is good. Now, if all your results were like this, it will be awesome, but I will probably be out of a job because this will be approved immediately without having a geotech engineer to have to look it. Most of the time, what I see is not that. What I see is this. So it's the same principle, right? So 30 inches is the radius of the shaft, but what you can see now is that you have problematic areas, especially at the bottom. Look what happened at the bottom. You have this coming down and decreasing significantly. So again, it doesn't mean that the radius is less. It doesn't mean that the shaft did this. Most of the time it could be, but most of the time what it is that the quality of the concrete at the bottom, it got mixed with sediments and you end up having a lower quality that did not generate the heat that you were expecting, right? It's a little tricky too, because just by the nature of what you're doing, trying to model the heat of, the flow of heat and doing the double integration, that your boundary conditions at the top and bottom are going to dissipate heat at a different rate. So typically it's what is called the roll-off effect, which is the bottom and the top will need to be corrected basically to correct for that exchange. So sometimes you could see that pattern of going like this and going like that at the bottom because of that. But in most cases, it's already corrected by the program and the software to avoid that, right? So in this case, for example, we definitely have a problem at the bottom because we see that all the cables came and gave us a smaller diameter. So we probably have sediments. Now, same thing we
I
can...
don't understand how
Mhm.
how the method can estimate the cover.
Because exactly. So what the method is doing is not estimating the cover. The method is estimating the entire radius, right? And then what you see on the plot is that what they call cover is just saying the equivalent radius minus the radius where you put your rebar. So it's not like what you see at the bottom of the plot is not a true estimate of the cover. It's just saying if I have an equivalent radius of this and I subtract the location of the cage, this will be my equivalent cover, but it's not a physical cover, right? So that's a very good observation that you did there, because what is shown at the bottom of concrete cover is not a true cover. It's just like an equivalent cover that you will have based on the equivalent radius, right? And this is the part that I say that sometimes it's a little tricky to understand, that this is not giving you a true physical radius. It's just giving you an equivalent radius of concrete corresponding to those temperatures, right? Regardless, what you end up having, obviously, is that you can identify areas that have issues. And as we said, the big sale of this is that you are measuring the entire radius and not only what is inside the cage. So then the question is, what do we do, right? Like if we have problems. So let's talk for a second. How do we evolve into this? We were doing CSL. We started doing CSL, I don't know, 15 years ago, 20 years ago. It was definitely a revolution. PDI, Pile Dynamics, and GRL, they produced this, and it was a revolution. Then we start looking into every single shaft that we had. It has the drawbacks as we talk, right? I mean, it takes time. It only gives you the cover, but it was still a very useful technique. Then they invented the piling, the thermal integrity profile, and definitely they replaced the product. So many people thought, okay, CSL is out, TIP is in. But, and I'm very glad that we did it this way. We start doing projects with both, right? Obviously, that's expensive because you are basically paying twice for similar testing. Then we went one step further, which is, let's not eliminate CSL yet. Let's put the CSL pipes. Let's not do CSL on every shaft, but let's have the pipes on every single one. Because what happens is, if I do a shaft without the pipes for CSL, I can never do CSL, right? If I do the pipes, I'm just paying the contractor to put some steel pipes or PVC pipes. That doesn't cost that much, but it gives me the option to go back. So right now, in most projects, that's the way we're doing. We specify having the pipes for CSL. We do not require CSL on every test because we have TIP on every test. And then what we do
but that requires the specifications not to specify which piles or number of piles that going to be
correct.
tested.
Exactly. So right now, basically, on the typical spec, what we do is you have to do TIP on every single one, and you have to install the pipes for CSL on every single one. You will get, as a contractor, you will get paid for doing TIP on every single one, but you will not get paid to do CSL on every single one. You will only get paid to do CSL on the specific ones that the owner is directing you during construction, right? So you will have an estimated at the beginning of the contract, but you will only get paid for those particular ones that you did CSL. But what that allows us is to have the option that if we find a problem with TIP, then we can go and do CSL, right? So that has been the way that we go. It seems to be very convenient, but then obviously that still doesn't resolve a problem. What happens if I see a problem in TIP? What happens if I confirm it on CSL, right? So this is the part that I love, because then it goes back to basics.
Are you supporting this idea that all piles should have cross-hole sonic pipes installed from the beginning?
No, I prefer to have TIP on every single one, right? And then have the pipes of CSL on all of them, and only do CSL on the ones that have a problem with TIP. So basically, if I identify a problem with TIP, then I go back and do the CSL, but only if I saw a problem, right? But if
TIP does not need pipes.
Correct, that doesn't need pipe. It's just that cable going in. It's faster and it's cheaper. Yes. So that's the way that I think it should be done. Now, if you have a problem on TIP, if you have a problem with CSL, if you identify an area of problem, if you have a depth that you have a problem, nothing will ever replace going and doing a concrete core, right? Because basically you just go and core the concrete and see what the problem is. Now, this is also that is tricky to understand, because typically people think that getting a core is going to show you what the problem is, right? But the problem typically is not on the core that comes out. The problem is when you don't have a core that comes out. My point, if I'm coring concrete, I should have a recovery of 100%, pure concrete, right? But if I do a core and I only get 60% recovery, that means that the remaining 40% was probably some kind of mixture of sediments and bad quality concrete that never made it out, right? That it was basically washed by the water that I was using on coring. So it's important to look at the cores that you get. It's important to do unconfined compression, but it's more important to look what was the recovery that did not come out, because that will be your clear indication. Now, for the ones that you got a core, obviously you should do an unconfined compression. You should see what is the quality. But many times you get a core and you see that it's all boggy, like a honeycomb structure. And that's the reason that you are seeing the problems, because the quality of the concrete is less. So now we go into this part, which is, this is the secret part of the presentation, Ahmed. This is the one that nobody ever wants to talk about. And you probably will never see a paper of this, and you will probably rarely see a person talking about this. And I love doing it because I'm a consultant. So I'm walking in the middle and I can point the problems without major liability. So what do you do on a drill shaft that you found problems, right? So the owner doesn't want to even share information, because basically what you're saying is you just paid for a drill shaft, extremely expensive, that have an issue. The contractor, it's a very uncomfortable topic, because what you're demonstrating is that they constructed something that is fundamentally wrong, right? So the only one that is happy to talk about is the consultant, because like, I didn't construct it, I'm not the owner, but I can point out your problem. So obviously the important part on these teams is to fix problems, right? That's
But
what we are here.
maybe you approved the wrong method statement.
Yes. But anyway, so let's see. So let's start with the picture on the right, top right. So this is what you should see. When you core, after you core, you put a camera, right? So okay, let's go slowly. You core, and once you core, you have to clean the shaft. You have to put a hose with compressed air. We typically put air at about 150 PSI. So you clean the shaft, right? You take all these sediments that come out, and you basically just try to dislodge. So once you do that, and this is the reason why I like to have a downhole camera on site, because even though it may have not been that useful during construction, it's extremely useful now. So once you clean this, you introduce the downhole camera. The top right picture, right, it's showing you what you should see. You should see a concrete tunnel, basically a tunnel of concrete, because you just did that. You remove a sample, so you should see a tunnel, and it should be concrete. Now,
So
the part that is,
one is inside the hole.
it's inside the drill shaft. Yes, you're going down inside the hole. Now, this is the interesting part, and these are the pictures that I'm telling you. You will see it on this presentation.
That camera is taking pictures.
It's video. It's live video as you go down.
Yeah, so it's not horizontally moving. The camera is vertical.
It's vertically going inside the shaft. So initially you should see this concrete tunnel, and as you go down, right, then because you already cleaned the sediments, look where you start looking. Let's say the middle picture on the right. That one, basically what you're seeing is the bottom of the shaft. You already kind of clean it. So you see the bottom. What you see at the bottom is the rock, is top of rock, or basically where this is supposed to be bearing. When you did the coring, you typically core concrete, but you also core rock to make sure that you have that break between the two materials, right? So right now what you're seeing is the bottom of this, and you are seeing that there is no concrete. In this particular case, it was like a sediment bubble, right? So you basically have nothing once you clean it. Now you can see things that are interesting. You can see the rebar, you can see the TIP cable, you can see the little boot that was put below the rebar, but there is absolutely no contact. More impressive, look at the bottom right. That one shows the rebar, shows the hole that keeps going on bedrock, but you literally have an area that there is no concrete. You have concrete, a void full of water right now, and bedrock, right? And then the one that I love the most, the one on the bottom left, that is supposed to be, because what you do is that you go with the camera and the camera looks down, but that camera also has the ability to rotate, right? And then you can look horizontally. And then that picture, the pictures on the right are looking down. The picture on the left, it's once you rotate the camera and you can see horizontally. That is showing you the bottom of the drill shaft. So basically what it's showing you is that you have bedrock, a void, and concrete.
That's a very interesting one, in fact.
Let me ask you this. We spent 20 minutes talking about new equations that tell us that we can increase the capacity for end bearing, correct? What is the end bearing? What is the end bearing? Zero. It's absolutely zero. There is no end bearing.
Zero, exactly.
You have a void. So that's the part that I say the new equations are aggressive for a reason, because you are making sure by doing this on every single shaft, you are making sure that you don't have this case, right? This is a drill shaft that was detected to be defective thanks to all the testing that we do based on LRFD methodologies, right?
Yeah,
So when we found this, you fix it.
it depends on the importance of the project and the amount of the loads. Some consultants and authorities now, they're forcing to have base grouting. So that solves the issue a little bit. Yeah.
Correct. And this is the part that I said at the beginning. Is this the first time that happened? Probably not. I mean, probably we have hundreds of shafts that have these issues before we just didn't have the technology to see the problems, right? So was that a problem? Who knows? When we were just designing for side friction, a problem like this, who cares? I'm not taking a bearing. So what I'm saying is what we did before was not wrong. What we did before was fine, given the tools that we have. And that's the reason that we have a higher factor of safety before. Once we switch into LRFD and we start optimizing, we reduce the uncertainty on the aspects that we can control. The quality control during construction is something that we can absolutely have a say and we can control. So by reducing the occurrence of these things, we are able to have more aggressive designs. That's really what we're doing today.
But you look
So
very happy in the picture.
I know, and that's the funny part, because obviously I was happy that I found this void. The contractor was furious. The owner was like, I never want you to tell anyone about this. And then I'm the only one that is smiling. So obviously I cannot tell you the location of the project or anything like that. But it's interesting because as the state of the art of the science, right, and our profession, it's interesting to see these kind of things. Now, how do you fix it? I mean, this is another problem on another shaft.
Yeah.
We basically is the same thing, right? So the way that we fix it is easy. Once we clean it, we just put, we just inject grout with Tremi, and we inject grout under high pressure, right? And basically we just fill those voids. We just fill
Yeah.
those pockets and cavities. So, it's a relatively easier problem to solve, even though it's a critical problem. Now, it's probably also very important to understand the cases where let's say that you have 100% recovery on the concrete and you don't have any of these voids of sediments or anything like that, but the quality of the concrete is lower, because that to me it's more complicated to fix. Because when you have that case, right, now you cannot clean anything. You basically have a concrete that is already there. It's just that it's not the quality you wanted. So on those, I have also developed different repair techniques that consist on doing like micro piles or something that is kind of retrofitting that.
It's very strange what you have shown here. Why do you think that happened originally?
I think it was because of the sediments. Like there was a lot of sediments coming because of the stream. This is also an extreme environment.
We did not see any sediments. We saw a cave with clear water.
Oh, yes, exactly. But then what happened, because these pictures is after you clean. You know what I'm saying?
This is after you clean.
Exactly. When you do the hole, the first thing that you have to do is to put the water under pressure to clean it, because otherwise you don't see
I can criticize also this by saying there were maybe rock pieces instead of sediments, and
exactly.
You also and they were maybe holding some load, no?
Correct. I mean, it's you can see rock pieces and rock fragments that are not sediment and are there, right? And I mean, some of those probably should have been clean. The mini seed probably didn't see them. I mean, the mini seed only covers 5 areas, right? Who knows if these were in the middle? But now, if you did not have the sediments, that concrete, those rocks and things like that probably will have become part of the concrete, right? And it will not have been that bad. In this case, obviously, the sediments and the sludge, it's really the main problem, because they don't, right? Now, I also have people that say, okay, so what if you have the sediment? Anyway, the sediment cannot escape, because basically what you have is a drill shaft with concrete and then bedrock, and then this is sandwiched in the middle. But if it cannot escape, it will just take the pressure, right? It will be like a fluid under pressure. But then that's a good argument. But if you have the slightest of a crack, then that sediment is going to go through that crack, right? So it's definitely an interesting subject. And then, as I said, this one is like more examples of that.
Was this project subject to dewatering while working?
No, because the problem is it was on a stream environment. So they find out that if they try to dewater, it was even worse. Right at the beginning, they tried dewatering, but obviously, as soon as you lower the water inside the shaft, you create a hydraulic gradient, right? Before
there will be a lot of flow upward
exactly
this time. Yeah.
Exactly. So the more you dewater, the more flow you get, the more sediments you get. So they decided just to maintain the water table where it was. It was a successful
But
project.
generally, the site was not being dewatered.
No, the site in general was not, because it was next to a river, so it was considered too complicated. I mean, keep in mind, we have, I don't know, 20, 30 drill shafts, and we only have problems in like 2 of them, right? So, I mean, I'm not saying that this happened on every single shaft. It's, it's when everything adds
Yeah,
and you have bad luck.
as you said, these problems are more critical when you have infrastructure.
Correct.
Because the number of piles in the foundation are less, and
It's
they
less
are
redundant.
critically used for holding the loads.
Exactly.
Unlike if you have a building with a raft
Yes,
on
correct. With a raft and a
300
lot of piles
piles,
and more
the load
redundancy built in. Yeah,
the load
correct.
can be redistributed between the piles,
Correct.
and
Correct.
also we usually ignore the soil or the rock to hold anything from the raft, but it also helps. So there are other benefits in having a large number of piles
Of elements, yeah.
that
Redundancy, it's
can
always good.
compensate these kind of problems. But
Correct.
if you have infrastructure, every single pile is
Matters, right?
important.
Yes,
Every
correct.
single pile is important. Yeah.
Correct. All right. So then, yeah. So then the last part on this is the cases that you don't have pockets, that is just the quality of the concrete. So typically what we do is, if we see that we have a problem and we cannot have the strength, we just do like a smaller pile, like almost like a micro pile or a mini shaft inside the existing shaft, and then just keep drilling and extend it a little bit. Those are more rare. We have a few that we have fixed like that. These are probably more common, but it's interesting. And what I always like to say, when we get contact in one of these projects and you feel the tension between the owner and the contractor, we always like to say, no worries. I mean, I know it's a problem, but we have solutions that we can fix this, right? And they are not even that expensive to implement. So not all the cases are that bad. Sometimes you see problems on CSL, sometimes you see problems on TIP, um, but we still have anomalies, especially in TIP, that you could see materials that are lower strength, but then you go and core. Like this is, for example, a project here in downtown Pittsburgh. We were working on a highway and we could only core the shaft at night, because this is literally drilling between like 3 lanes going in one direction, 3 lanes going in the other direction. So they only let us drill at night. And in this case, we thought we had a problem, but then we went and drilled and all that, and we got a 5 foot recovery with all the unconfined compression being fine. So I always like to mention that not always when you think you have a problem, you have a problem. Always keep in mind we're using numerical tools and analog techniques that sometimes have like false positives, right? So it's important to be aware of that. And then this really takes us to the ultimate of all the ultimates, which is the O cell. And the O cell test, it's the ultimate because it's actually a load test that you can do. Most drill shafts, you cannot do load test in regular, let's say a static load test, because the size, right? I mean, I have done drill shafts that are 12 feet diameter, 80 feet deep. Like imagine the frame that you will need to test something like that. I mean, what will be the hydraulic jack that you will need for that? So the O-cell test is a technology that was invented by Osterberg. Uh, it had a patent for many years. The load test was the company that had the patent. The patent since then has expired, and now basically everyone can do this. GRL, PDI have a very good product that is called the bidirectional load cell. There is different companies in China that are also now offering these cells. You can still do it with load test. They have a lot of experience on this. And basically what it is that you have a shaft and you put a cell in the middle, that it kind of works as I like to make the analogy with an Oreo cookie, because it's basically a cell that is there and it opens. And what it does is that the cell pushes part of the shaft up
But
and
the
part of the
cookie we
shaft down.
eat, this one
The
we
cookie
cannot
you eat,
eat.
don't even try to eat this.
We can't eat this one.
It's a very expensive cookie too. So yeah, so this opens and then you will see the upper part has the weight, the own weight of the concrete that is coming down. But when you push up, you develop the side friction going down, right? Typically, these shafts work on side friction going up, but during the test, the side friction is going to go down. So you have a balance on the upper part, which is you are pushing up with the cell and you have the weight and the side friction coming down. And then at the bottom, you have the cell pushing down, now the side friction going up and the end bearing going down. Something that is extremely important on this is you are not really testing the ultimate load. What you are trying to test is the ultimate a stress, right? I don't care about the total load. What I want to see is the stress. What is that shear strength that I get? It's basically a stress, no force, just a stress. So the way that you do it is that you balance it, right? And you do the calc, making sure that you are mobilizing the ultimate strength on the upper part and the lower part. This is the way that the test looks. It's an interesting test and it's an expensive test. Um, the first one that I did in my life was $500,000. This in particular, obviously, as the year pass becomes cheaper, this one was 350,000. Um, and it's an interesting test. I mean, it's a sacrificial shaft, right? So you have to drill it, you have to construct it, you have to put the rebar, you have to do the CSL, the TAP, everything that we do. And
Yeah,
in
well,
that part,
it doesn't need to be sacrificial.
well,
You
it
can
typically is
grout it. You can grout it and use it. But if
correct,
it's a
correct,
preliminary test, like
exactly. But
like it
typically
is
end up
before
being
the project, so
exactly.
that's different. Yeah.
Now, and always we need to keep in mind that you probably took it to an ultimate strength, and you probably went to peak to residual,
Of
right?
course,
So
that
yes,
if you reach failure, that's fine.
exactly. But I agree with you. Typically, we just grout it, and then you connect it even to the footer. It's just that you are not accounting on the strength that it comes, but it definitely will provide some resistance, right? So that picture, you can tell I have a huge smile because for me, this test was huge. Just as an anecdote, when I started working at the company that I work, on the first week, on the very first week, they were doing an OSIL test. So they sent me to take a look, right? And you know how I am, and I'm extremely proud, and I take the selfies and I take the picture at the site and all that. I thought wholesale tests, it's something that we were doing like on weekly basis. So I didn't even bother to take a picture. I was like, oh, I'm sure this test is
Come on,
done.
yeah.
And because I didn't understand, I didn't know that it was so unique. So I didn't take the picture. And it took me like 10 years until I have the chance to do to another wholesale test. So as
How much was the load on this one?
this one, we end up going, I think in a second I'll show the plot, but it's about 9,000 kips, 9.3 thousand kips.
Hmm.
So, okay. So then you have the sail. So obviously you have the sail towards the bottom. These are just pictures of like a close up of the sail. You can see the TIP. You can see the CSL. Obviously we have strain gauges and telltales and all kind of instrumentation to see the formation, right? Because you want to do this test monitoring absolutely everything. As we mentioned before, you are measuring the ultimate, right? The ultimate strength. It's a very simple calc, but you have to be really careful because if you messed it up, you just wasted, $500,000 or a little less. So it's basically just saying, okay, I need to make sure that the sail has the capacity that when it opens and it's in full force, I'm taking the skin friction to the ultimate or higher than the ultimate.
Well, the
The
figure now is less, I think. It's not half
yes,
$1 million anymore.
yes, no, it's going down. It's going down.
It's
It's
going down a
significantly,
lot.
but you still need to check your calc. So, and in a test like this, you're making sure that you are failing in side friction. In end bearing, you are never really gonna fail, but you just want to make sure that you get close or if possible higher than the end bearing that you assume on your design. Uh, then after that, it's the construction. The picture on the right for me is awesome because you don't get the chance to see the O cell going in the hole, right? It's drilled, it's ready, and the shaft is going down. You can see the O cell. There is some close-ups there, even when you lift it. It's a very unique opportunity, and actually, I'm gonna be doing an O cell in a few weeks, actually. So I'm very excited about going to that one too. Um, and then
Where will be that one?
that one actually is closer to Philadelphia, so it's gonna be interesting. Yeah, it's
I can't fly to you.
absolutely, you are more than invited to come. You are more than invited to come here.
Let's say.
So this one is what happened. So you construct it, and this is very interesting because when you construct the O sail, there is all kind of excitement because you see the sail, you see the shaft goes in the hole, and then you are supposed to wait like 7 days just to make sure the concrete is hard. You do the TIP, you do the CSL, make sure that everything is in place, everything is working, and then you come and fail it, right? So every time during my life, I always enjoy load testing. I mean, I do a lot of load tests on piles, auger cast piles, micro piles, any kind of foundation, any kind of deep foundation. And I love going there because you see the frame and you see the load. And as a designer, it's seen that things are taking the load that you designed them for. So obviously, like in this particular case, I got all excited because I was like, I'm going to see this. However, when you show up on the site, it's the most an inspiring test that you can do, because there is no load frame. There is nothing that you can see. You just see like a rental car with a lot of hoses connected to a laptop in the back of the car, and that's
Yeah.
it. Everything is done with hydraulics, right? So it's very different than any other kind of load test. In this
You know
particular,
what you need to invent now? You get
yes,
a patent for that one. It's
exactly.
something for lateral loading. Now they are splitting the pile with a nocell.
Yes, yes, yes.
Putting
Okay.
the nocell like that in the middle and splitting the
And
pile.
split it. Yes, correct. It's put it horizontal and do that.
Or
So
maybe
yeah, so
they're putting it somewhere.
yes, that one is more interesting because you at least you
I,
see some
I
action.
wanted to invent some kind of cells or jacks that can push the pile laterally
Hmm.
without the need of another pile for the
Yes,
reaction.
correct. Like a reaction. Yes, yes,
Yeah.
yes. Correct, correct. So, but in the spirit of keeping the excitement high on this project, you can see that I have a piece of paper on my hand, right? So I said, hey, why don't we do this? I'm very confident on the calcs that I did. Let's see what is the maximum load that we're gonna have. And why don't each of us put a value of what do you think is gonna be? And then we put like $10, right? And then whoever wins all the money, right? So people actually got excited. The operator from the load test was like, all right. He said, I do this test all the time. So I think I have a good idea of how much it's gonna take. So everyone started getting excited and we start putting the money and all that. And then the engineer from the state came and say, no, you guys cannot gamble. That's illegal. You cannot do this in a public site, right? So we return the money to every person, but then I say, but still, I want everyone to have a prediction of the test before the test is done, right? And then I
But
put my name.
it's more interesting if it was gambled on it.
Yes, and believe me, I could have done a lot of money. So everyone put the value, and then this is the actual test. This is what is called the butterfly diagram, because it's basically you are seeing the results. It's not that easy to see at the beginning, but once you go slowly, you understand. So what you have on the x-axis is the load. So that's the load that you are applying. Remember, that load goes up and that load goes down, right, for the different parts. What you see on the y-axis is the displacement. So what is above the zero is the displacement of what it was above the cell, and what you see below is what it was below the cell, right? So let's start with the top one. So you can see that we incremented the load and went to about 9,000, and then we stop and did a creep test. But at the moment that we stop, you could see that the deformation continued. So that means the upper part was already starting to fail. It was not holding the load, right? Now, the bottom part, it's not moving. I mean, the bottom part has no issue. It's just that obviously this is an action reaction system. If I lose the support, then I'm not able to put more load on the bottom part. I will not be able to fail the bottom because the upper part start failing already. So we did the creep test, and then after that, we continue to increase the load. And as soon as we start increasing it, boom, it failed. I mean, it just basically went up and it completely relaxed. It did not take any load. It completely went down. So we failed the upper part, but we were not able to fail the lower part because we lose the footer above. I mean, no reaction. Now, the values themselves are fascinating because I predicted on that little piece of paper using the ultimate strength, I predicted a capacity of 9,300 kips, and it failed at 9,371 kips. That is an insane prediction within 1%. I also predicted a deformation of 0.4 inches based on the fact that we know, as we talked at the beginning of the talk, that peak is going to be mobilized close to 0.5 inches. The reason that I put 0.4 is because I said 0.5 is kind of the limit. I like 0.4. 0.4 is the value that I use to determine when I have down drag. I have grown seeing a value of zero point 0.4 in interface test between like geogrids and soil. Is the same value I use for steel piles. It's a value that comes from my stomach. I mean, it's basically God's feeling. There is no calc on that. It's just a value. And then the actual measure was 0.3. So it was extremely interesting. Everyone looked at me at that job site like, wow, you really know what the hell you're talking about, right? And to me, it's like, well, in reality, it's not my credit. I mean, I'm just using the equations that are on the AASHTO manuals. I mean, this is what it's all about with LRFD design. When you
But
control the
you're using
construction,
them correctly.
correct, exactly. So if you understand them correctly, if you use them correctly, and if you make sure that you have all the quality control that is required, you
And
can
also
get
credit to the lab tests.
Exactly, and the lab testing to
If the
make sure that
results are
everything.
done in a good quality,
Hmm.
and the tests were also based on the standards carefully.
Yes, exactly.
This 0.31 is close to 0.5% or what?
No, the 5% was
You
actually
said
bigger,
zero point 0.5 inches.
to the 0.5 inches. Yeah, so that's the
zero point
reason I
0.5
was going.
inches, I'm not happy with that one.
Correct. So that one seems to be a little higher, and that's the reason that I wanted to go with zero point 0.4. It ended up being a little less, right?
How about the diameter? What was the diameter of this
It
pile?
was 11 feet. No, sorry. No, this one wasn't 11.
Diameter,
This
diameter.
6 feet. So it was 6 feet diameter. So if I calculate 5% of that, it's gonna be about 3.6 inches, right? So yeah, so you are still very far from that 5% diameter, but that's supposed to be the ultimate on end bearing, and we were really far. I mean, based on the plot and all that, we were far from being at close to the end bearing failure. Like if you look the plot, if you go back to
Well,
this plot.
this is still it's not complete skin friction failure, but
Mhm,
it looks like you have you have more movement at the top.
correct.
Well, it's just strange because usually like 1% you need to reach of the
Mhm.
diameter for failure.
Yeah. So it's interesting results, and it proved like using this equation and all that. So we
Yeah.
wrote at that time. We wrote a paper that was called "Predicting Drill Shaft Capacity. Are we close?" And obviously the conclusion was yes, we are close, right? I mean, within 1%. So after I did this, I did this presentation, and I start going. I got a lot of invitations around the world because obviously it was extremely interesting. And I think I was presenting this in Sao Paulo, Brazil. It was the keynote lecturer on a conference there. And then somebody raised their hand, right? And said, that's a great result. But you realize you have one result. You know what I'm saying? It's like you are basing all this conclusion on one test, which I understand. I mean, obviously, when you want to.
You can work with me on that one. I've done lots of OSLs.
Excellent,
Yeah.
excellent, and we need to take a look at that. I mean, after that, I also look at different also. Like I work a lot with the Deep Foundation Institute, like Superpile that you were attended a few weeks ago, and then we start looking also into this, right? And then we found a lot of cases, and for most of the cases that I have seen, is the same behavior. I mean, the new limits that you get on the ASHTO LRFD manual tend to be very accurate. I mean, we have a few that we have determined.
Is there now a part in ASHTO talking about OSL?
Not yet, but I predict that it will be very soon because I think we have enough O-cell tests that we can even have a good database. And I think that kind of database should be shared. Let me put you an example. I was working on a project a couple of years ago in Pittsburgh downtown for a private project there. And then the owner, because this is like through the city of Pittsburgh, they gave me access to a lot of O-cell tests that were done for construction of the new stadiums and stuff like that. And obviously, the idea was to use those OCL test results in our design of drill shafts, right? And it's interesting because what you are seeing is that many OCL tests are definitely satisfying the value by ASHTO, but they also are a little higher than that. So
Usually they're higher, yeah.
yeah. So I think we're in a good path. It could be a little maybe more aggressive. I think we still need to
Well,
understand a lot.
it's not only capacity. You need to take care of deflections. I mean,
Yes, correct.
settlement.
And that
Settlement
probably will
usually
control.
is a more controlling factor than
Yes.
capacity.
And I think also not all rocks are the same. Like this particular example, this was in a good quality. It was a
Exactly.
it was like a shaly siltstone material, right? Um,
That affects a lot. Yeah.
yes. So I think but it's definitely encouraging. I mean, we're definitely going into the right direction. So
Piles are now very important because there we have these very good quality control tests, cross-hole sonic,
mhm.
integrity tests, dynamic tests, OCell tests. You can use now the piles for thermal
Oh yeah, thermal piles. Yeah,
circulation
thermal
of
exchange and
water.
cooling and yes,
There
yes,
are
yes, yes.
lots of pipes and lots of reinforcement and lots of wiring inside these piles nowadays.
Yes,
And
yes.
and this guy will be something in the future.
Yes, exactly. So yeah, so I mean, the technology keeps evolving, and there are different applications. most of the
This
applications
is
that we...
during COVID or what?
Yeah, this was during COVID. This was during COVID. So yeah, so there is many applications. The one that we covered for the most today is the axial resistance, right? Axial resistance of shafts. We also talk about lateral resistance, being able to take lateral load. So that's one of the main applications. Uh, but I always have to show this. So this is a project that I work in Colombia, and it's a very tricky project. It's called the Chirajara Bridge, and it was a collapse. I was not involved on the design. I was just involved on the forensic investigation because it was a collapse. Um, Unfortunately, 10 people were killed during the collapse. So the picture that you see on the left is me doing the geotechnical investigation days after the collapse. As I
So
mentioned,
where did the collapse happen? Is
so the
it in the piers?
yeah, so the collapse was on the piers. The structure is it was a three-span structure. It has abutment one, then they have what was called Pila B, which is like pier B, which is where I'm standing on the picture on the left, and that's the pier actually that I'm also inside on the picture on the right. And then what you see on the far on the left picture, it was the second pier, and then the other abutment, and then the collapse occurred on the pier B. They were still not joined. I mean, it's a straight cable,
They
bridge.
did not join yet.
They did not join yet. They were very close to join, but not yet. And then what ended up happening is that it failed during lunchtime. Most of the workers were not at the bridge. They were having lunch, but there were 10 people at the bridge because they were doing welding. And unfortunately, those 10 lives were lost when this collapsed. So because of the experience that I have with drill shafts and also the fact that I'm from Colombia, I end up being invited through different companies to participate into the forensic investigation to see if geotech was the cause. So the reason that I always like to talk about this is it was not the reason for the collapse was not geotech. The reason for the collapse was a structural mistake because I was involved on the litigation of this and I was involved on on the forensic investigation and expert testimony. I cannot talk about a lot of things, right? On the
No, of
structural
course.
aspect.
This is maybe still ongoing.
Exactly. But I can talk about the geotech part because the geotech part was far from being the reason of this. Fortunately they have instrumentation. They have inclinometers inside the walls of the caisson, and they have
Mm,
in front and behind. And you can see that
marvelous.
when the collapse happened, nothing moved. The geotech part, I mean, during the collapse, obviously, if you have a collapse of a bridge, it moves like a very tiny amount, but it was nothing related. Now, the reason that I want to bring this into the presentation or the talk today is because it also shows how we keep evolving the concept of caisson. Uh, Based on what I just showed before, it kind of gives the sense that we know everything about caissons, right? And we know the testing and we can predict capacities. But then contractors, right? They are reinventing the wheel. So this is a technique that is being used now in Colombia, which is hollow caissons, right? You never hear about a hollow caisson in the US for infrastructure. And it's basically a hollow caisson that this in particular had end bearing, side friction. It has anchors on the back. So it was kind of attaching it to the mountain. And it also has micropiles at the bottom as a ground improvement technique. So I end up testing all these anchors, and it was quite an experience. I mean,
And
it's
this remains open uh, during the life of the structure.
correct. It was supposed to remain open during the life of the structure. The access though was not that good. When I went there, I have to go down rappel. Like they only have like a 1 foot by 1 foot or 2 feet by 2 feet square, and then you have to go down rappel, and they have like a ladder, like a basically just like in the wall that you have to go down. And it was extremely, I mean, I'm not into extreme sports or anything like that, so it was quite experience. Then after that they put like the scaffold and it was easier to go up and down. We end up testing all the anchors, and basically we demonstrated that it was not a failure of geotech. But to me it's interesting because how do you design one of these caissons, right? I mean, how do you do end bearing? How do you do side friction? It's a lot of questions that open, that is like, as contractors keep reinventing the wheel. Obviously, when we did this investigation, we developed ways to analyze skin friction, end bearing.
Well, this is
This
not a standard foundation.
It's not
It
a
should
standard, but
it should be treated in a special way.
correct. And this actually had a lot of analysis on like Plaxis 2D and 3D. They also have analysis with rock science software and slide. And I mean, it was designed the proper way. Unfortunately, the bridge collapsed, and that is always going to bring like a bad name to the project, right? But this was a very ingenious way to do caissons. So I think in the future we're gonna see more of this, and we probably are gonna develop codes and things like that that start including this type of caissons, right? I mean, this
Yeah.
caisson was huge. This caisson was 24 feet diameter with 3 feet thick walls, right? It's a whole new way to construct things that we were not used. So I always say that South America is an awesome laboratory of geotech because not only the materials that are there, but it's also the techniques
The
keep
techniques
getting
are
reinvented.
advancing. Yeah.
Yes, and obviously, unfortunately, as it sounds, in developing countries, the regulations are not as strict as in North America, so they give more freedom, and you can try things like this. In this case, the geotech was not the cause, right? But definitely we're trying something different, right? In some cases, you tried something different and it may not go as well, but in this case was all good. I have the chance to go inside the case, and as I say, on the B, and then I also went into the other one. So these pictures are that. The caisson itself was constructed by hand. They basically went into the rock with a jackhammer. They were
Yeah.
breaking the rock, taking it out with buckets, and then just doing like casting plays for the rings, and they can continue going down. They installed the anchors as they were going down. So it's just interesting concept that I like to share because I think the future will go in directions like that. Other applications of caissons, we talk about this on our previous talk. So I think that's the reason this talk and the previous one we did complement each other very well. We talk about this case, which is using caissons as a slope stabilization technique. That's something that we have done extensively in the past. This is another project. I think at the time that we recorded the previous one, I don't think we have this project. This is kind of one that is going here in Pittsburgh that we are doing caissons to stabilize a landslide. And then obviously, I have some articles in these kind of topics because obviously I love them. So if anyone want more information, I always invite them to connect through LinkedIn. I
Is this DFI?
So these two are from DFI. Yeah, we published them with DFI. These are DFI has something that is awesome. That is all the articles are free, right, on the DFI magazine. So if anyone needs the links, just let me know through LinkedIn. We can connect, and I can pass you all this information. And I think that's all I have really for today, Ahmed. So I mean, obviously, thank you very
I'm
much
very
for the
glad.
opportunity.
Very glad to see you again with me.
We
I,
need to
appre-
keep doing
I,
these
I
things.
I appreciate it really, and the information it was marvelous. I liked it so much.
No,
Thank
thank you.
you.
We have a lot more topics that we can record in the future. I mean, what I see is that every time you and me talk, man, this goes for a while.
It's very beautiful subject, and uh, you have given a lot in this presentation. Thank you very much, and I hope you will accept to
Absolutely.
record something again.
Absolutely. We need to keep going with all kind of topics. We need to keep talking about ground anchors and geotextiles and how to implement them on different software and things like that. So we still have a lot to talk.
Yeah. Thank you very much, Sebastian.
All
Have
right,
a good
Ahmed,
day.
and everyone listening. Bye.
Bye bye. We need to go now. Bye.